Hey everybody, I want to take a look at this practice quiz. And buried in this practice quiz is going to be something else that we covered in class today, which is derivation of the range formula. So I'm going to actually begin with the first part here. I love this question. We have a faucet. Let me just draw the faucet. Steel faucet. Here we go. Look at that. And there's a little spouty part. Look at that. We go like a little... Okay, you know what, that's the best is we're going to do for a faucet. So, and then we have this little drop of water, okay? And what we're saying is that we have one drop that's already fallen, right? And then 1 second later, so this is drop number 2, and this is drop number 1, and we want to know what happens as the drops fall. Do they move further apart, move closer together, or maintain a constant distance? And we're going to prove our answer algebraically. So let's look at drop number 1. Okay, so x of drop 1 at 1 second is going to be 1/2 g times 1 squared. We're going to treat downwards as positive. So x of the first drop after 1 second is going to be basically 5 meters below the faucet. Now let's look at drop 1 after 2 seconds. Okay, so x1 after 2 seconds is going to end up being 1/2 times g times 2 squared. Okay, so that's going to end up giving us 5 times 4, which is 20 meters. So now let's do a little comparison. At t equals 1 second, drop 1 is at 5 meters, and drop 2 is at 0 meters. Now, at t equals 2 seconds, drop 1 is now at 20 meters, and drop 2, having fallen for 1 second, is only at 5 meters. So look, we started off with a separation of 5. It's now become 15 meters. So what this tells us is the drops actually move further apart. All right, so there we go. Now let's take a look at question number 2, which is going to be the derivation of all the formulas for projectile motion. So I'm going to launch at a speed v0 and an angle theta. And I'm going to write these, actually I'm going to use a different color here, so I'm going to launch here. And I'm going to launch at a speed, we'll say v0 and an angle theta. And the idea is that these two things are our knowns. So let's begin by getting the height. So to get the height, I'm going to use the following formula. And I'm going to note here that v0 in the x direction is v0 cosine of theta. And v0 in the y direction is v0 times the sine of theta. So when we go ahead and we get the height, we're going to use the following formula from AP data booklet, or from the AP formula sheet, which is v squared is v0 squared plus 2a x minus x naught. Thing is, that's not really helpful for this vertical height that we're trying to solve for. So let's be clear. When we're dealing with the vertical distance, we really have the y variable to talk about. And we have gravity pointing downwards, so we're going to define downwards as negative. And so that means g is going to be a negative number here. So I'll just write it as a negative g here, times y minus y naught. And let's be really clear on what we know and what we don't know. So we know that at the top the speed is 0, At the bottom, we're given v naught sine of theta squared minus 2 times g. And our unknown is this height h. And of course, our y naught is just 0, the ground level. So when we actually isolate h, we're going to end up getting v naught squared sine squared theta all over 2g. So that's our height formula. And once again, let's just remember our goal. Our goal is if I give you a launch speed and a launch angle, you can get me height, range, and hang time. Moving on to the idea of hang time, let's go ahead and do that now. So for the hang time, I'm going to actually use the formula v equals at plus v naught. Once again, true but not completely helpful. So at the top of the trajectory, I have a speed of 0, negative g times my unknown time that I'm going to solve for. And v naught is a known. That's v naught times the sine of theta. Now I'm going to isolate t here, and that's going to give me v naught sine theta all over g. But the thing is, this is just the time up. We need to double it to get the total time. So when we double it, what we're going to end up getting is the hang time is 2 v naught sine of theta divided by g. All right. Lastly, let's go ahead and figure out what's happening in the horizontal direction. Now here's the interesting thing. In the horizontal direction, let's just note, there is no acceleration horizontally. So what that tells us is that in the x direction, we can simply write x is v naught xt plus our initial position, which is going to be 0. So we're going to end up getting that the horizontal position is v naught cosine theta times t, which is the total hang time, and that's going to be 2 v naught sine theta divided by g. When we go ahead and actually kind of put some letters together, this ends up getting us v naught squared, 2 times sine theta cosine theta all over g. Now there's a double angle formula you might not know about. It turns out this is equal to the sine of 2 theta when you check with trig. And so our total range in this problem is given by v naught squared sine of 2 theta divided by g. So that is our derivation of height, hang time, and range. I hope that is helpful.